There are two chain rules in calculus for taking the derivative of functions. One is for taking the derivative of a product of functions, and the other is for taking the derivative of the function of a function. And this little screen cam presentation is about the chain rule for taking the derivative of a function of a function. Suppose we'll start with a function f of y. And I want to do it by example. Let's say f of y is equal to the sine of y, where y itself is a function of another variable, x. I'll call y equal to x squared. So our f of y being equal to the sine of y can be expressed if we substitute x squared for the y. This is equal to the sine of x squared. So we clearly see we get a function of a function. To take the derivative of that, according to the chain rule, the derivative of f, which is a function of y, which itself is a function of x, so with respect to x, is df by dy times dy by dx. These are not ratios, but this represents the derivative of f with respect to y. But if we looked at them as just algebraic ratios, we could see it's as if the dy's just cancel out, and you're left with df by dx. So let's go ahead and do it in our example. df by dy in this case, where f of y is just the sine of y, would be the cosine of y. And then we got to multiply that by dy by dx, but dy by dx is just 2 times x to the 1, or 2x. And we can express that strictly in terms of x, as the y itself was x squared, so that's the cosine of x squared, all times 2x. Now, I generally do that in a little bit of a shortcut. We could say the function that we're trying to take the derivative of, I'll call it g of x, which is just f of y, and hence is the sine of x squared. It's dg by dx. It'll be the same thing as df by dx, since it's what we took the derivative of before. I can look at this. This is the sine of an argument. The argument is what you're taking the sine of. And I can say that's just the argument we called y before. So taking the derivative of the sine with respect to the argument is taking the derivative of the sine with respect to y. Just look at this as the sine of y, and that would just be the cosine of y, or the cosine of the argument. So I just have the cosine of x squared. So I take the derivative of the sine with respect to its argument, so looking at that as if it was just one symbol. And then times the derivative of the inside, times the derivative of the argument, which in this case is 2x. So it goes a little bit more quickly. You can do it in one step, thinking about taking the derivative of a function. So let's look at a different example. Suppose g of x is equal to, say, the exponential function of 3x cubed. And we want to take the derivative of that with respect to x. So it's the derivative of the exponential with respect to its argument, which is just the exponential. Remember, if you get e to the y, the derivative with respect to y is just e to the y. So I'll just write down the exponential function of its argument, and then times the derivative of the argument. The argument itself is a function, and that, let's say we bring down that 3 times 3, we get a 9. So it would be times 9 times, we'll lower that by 1, so we get a 2, so it's 9 times x squared. As our dg by dx. For another example, suppose we've got g of t this time. Let's make it a function of t is the natural log of the cosine of t. So we take the derivative of the natural log with respect of its argument with respect to its argument, so it'll just be 1 over the argument, or in this case 1 over cosine of t, times the derivative of the argument with respect to the variable we're trying to take the derivative with respect to. So the derivative of the cosine of t with respect to t is minus the sine of t. And that's interesting. Sine over the cosine is just the tangent, so you get minus the tangent of t as dg by dt. Should emphasize that's what we're doing here. We're taking the derivative of that function with respect to t. And that's probably enough examples, so we'll call that the end of this screen cam presentation on taking the derivative of a function.